This afternoon will be the resonance and tubes. Today in class, we are going to talk about damped harmonic oscillators. Now, what is a damped harmonic oscillator? Let's start with a harmonic oscillator. Do you remember what a simple harmonic oscillator is?
That a wave that's oscillating with another wave is anti-frequency.
No, that would be something like resonance, which I got this set up and we'll do lab.
Then I don't remember.
Simple harmonic oscillators are when you have a restoring force that's proportional to displacement. So the example of a mass on a spring is an example of a simple harmonic oscillator.
Okay, I remember that now.
So
is that the same for a pendulum or just the spring?
It's the same for pendulum. If you have small amplitude pendulum, it's also a simple harmonic oscillator. Because the restoring force, which is in that case G sine theta, mg sine theta, is proportional to theta for small angles. And that's a simple harmonic oscillator. And we will start our work by examining the simple harmonic oscillator, which is really quick. And then we're going to go to a damped simple harmonic oscillator. What does damped mean? I'll give you an example of a damped simple harmonic oscillator.
I should just lump those faucets.
Yeah, well, you know, beggars and choosers.
True.
So here we have my mass. Good morning, Randy. And so like this is undamped.
Right.
But if I put this in the cup of water, I apparently have to lower it more because I forgot to take into account the buoyant force. Right? It's not stretching the spring as much because of the buoyancy.
Right.
So now, notice it's going at a slower rate and it's slowed down to stop. So that's damping. A damped simple harmonic oscillator is a simple harmonic oscillator that has something that's taking away energy. So this is exactly what a shock absorber is in your car. Your car has a spring system, right? Old school, you had those springs that were a bunch of pieces of iron bound together. Newer cars, they look like this. The purpose of those springs is so when you hit a bump, your tire goes down and up, and the car stays reasonably constant without lurching up and down. But the problem is if you have the tire set on springs, if you hit a bump, then your car's going to oscillate like this down the road.
Because it doesn't damp, therefore it doesn't slow down.
Right, it would just keep going up and down. You would have energy lost over time, but it would take a while. And so the idea of the shock absorber is to damp it so it only does a few oscillations. So you can test, how good are my shock absorbers? The basic rule of thumb I was taught is you go and you press down on a corner of the car, and then we let go. If it oscillates more than 3 times, your shocks are shot. If it comes to rest in less than 3 oscillations, then you're probably okay. That's the rule of thumb I was taught. So this is an example of a damped simple harmonic oscillator. So that's what we're looking at today. So let's start by looking at the undamped case. We call the hanging thing a bob, and we're doing the case if it's not in water. You see my picture exactly correlates to what we have set up here. So if there is no damping, we start with Newton's second law, and we say sum of the forces equals what?
Sum of the masses times sum of the forces is mass times acceleration, or is something more specific?
Yeah, mass times acceleration works perfectly for me.
Okay.
So sum of the forces is mass times acceleration. The more specific one is that. dp dt. But for our purposes today, the mass will be constant. So A, which is d second x dt, is fine. So now if we look at this situation, we have to, number one, be very careful about our directions. So the first question is, what direction do we want to consider positive? Up or down? Okay, so we're going to consider up positive. And so if I do the sum of the forces, I'm not going to put vector signs. I'm just going to put positives for up, negatives for down. So if I, for instance, let's say I take the spring and I stretch the spring down. So if I stretch the spring down a distance of, x is a negative value here, but it's a distance of x. Actually, you know what? I'm going to do it up so I have a positive x. So I'm going to bring it up here. The reason we usually don't show these as verticals is because we have gravitational force we have to consider here as well. But if I lift it up, my spring, if I consider x equals 0 at the equilibrium position, then what direction is the spring pulling or pushing if I lift this up?
In what direction?
If x is positive, if I displace it upward from equilibrium,
Right.
then what direction is the force of the spring?
Isn't it also upward? No.
The spring, let me grab this one here. The spring pushes the opposite direction that you displace it. So if I squeeze it, it pushes out. If I extend it, it pushes in. So in this case, we've squeezed it, it's down. And so we're going to have a downward force, so minus kx. And then, of course, we do have gravity, which is also downward, so I'm going to put minus mg. And that is it, right?
Yeah, I guess.
And so that's going to be equal to m d second x dt squared.
D second x?
Right, because acceleration is the second derivative of x. So now if we rearrange this, we're going to have d second x dt squared plus k over m x equals mg. What I did is I put it so I have the things that have x in them on the left side of the equal sign, the things without x, which is just mg, on the right side of the equal sign. And now the solution to this is, well, you have two solutions. Neither of you have taken differential equations. Is that correct? Okay, so you have the homogeneous solution, which is the solution you would have if this net force was equal to 0, or if this equation to the left side was equal to 0 instead of equal to mg. And then you have the particular solution. The particular solution is just basically going to give us a constant offset here. We're not going to look at the particular solution, so we're going to do just the homogeneous solution. That is, we're going to solve d second x dt squared minus k over mx equals 0. That's the homogeneous equation. And you don't know how to solve this, am I correct? It's a second derivative. If it was a first derivative, what would you have done? First would have separated the variables, then integrated. For a second derivative, well, that's something that we haven't done. And so the way we approach this for a class where you haven't taken differential equations is we say from differential equations, we know the solution to this has the form of x equals e to the bt. And so if the solution has that form, then I plug it in and I find what b is going to have to be. So if I'm going to plug this in, the first thing I need to do is find the second derivative. So what does it mean if I put a single dot over it?
First derivative.
With respect to? Time, right. So I take the first derivative. What's the first derivative of e to the bt?
B even BT.
And then what's the second derivative?
B squared E to the BT.
And since e to the bt is x, I could write those as bx and b squared x. So now I'm going to plug those into my differential equation. So I'm going to have b squared x minus k over m x equals 0. Which can be
Wait. B squared X is
d second x dt squared.
Okay, yeah, that makes sense.
And now I have a sign error. How do I have a sign error? I have a sign error because I can't copy a sign. That was a plus sign there?
It should be minus, right?
No. It should be plus, but I wrote minus. When I get to this part of the derivation, I'm like, uh-oh, that's not going the right way. Now it's going the right way because I have the sign corrected. So there are two situations that would make this true. So Randy, what are the two situations that would make this true?
I'm lost.
Okay, one of them would be if x equals 0.
Oh, you mean?
Oh.
Yes.
If x equals 0, that would be true.
And then the other one would be if b squared plus k over m equals 0.
Right. But x equals 0
changes this.
Right.
X equals 0 we call the trivial solution.
Okay.
Because what would it mean if x equals 0?
No.
No movement. That's trivial. We haven't really solved the problem, right? We just said, well, if it's stationary at the equilibrium position, then everything works out.
Right.
So we focus on the other one. We just throw out the trivial solution as not useful. It's a solution, right? It's a true solution. It would be dumb to say it doesn't exist. But for the non-trivial solution, we have to have b squared plus k over m equals 0, which means b is equal to the square root of minus k over m. Now, k is always a positive value. And of course, m is always a positive value. So b is the square root of a negative value. Now, when you were like in 4th grade, what did your teacher tell you when you had the square root of a negative value?
Impossible.
Yeah, in 4th grade, they said it's impossible. Of course, you've had more education and range, you've been doing a lot of these kinds of things recently. And so it's imaginary.
Yes.
And if you read Calvin and Hobbes, Calvin asks Hobbes what an imaginary number it is, and he says, oh, it's something like 11 or
I need to read about Calvin Hobbes. I don't remember that.
Now, there's another thing I did wrong here. Can anybody spot my mistake?
Plus or minus.
That's right. So there's two possible values for b. So I have plus or minus I square root k over m. Well, to make life simple, you know what we're going to do? We're going to identify omega is equal to the square root of k over m. Does that look familiar? Because that's exactly what we said. And I said, in calculus, this is kind of trivial to get the solution, that omega squared root k over m. Now we have that. Without calculus, it's all hand waving. But what does this mean? Going back to our form, it's now, our solution is e to the plus or minus I omega t. And so we have two solutions there. We have solution 1, and we have solution 2. And our true solution has to be a linear combination of the two. That is some constant times x1 plus some constant times x2. And so we say that our actual homogeneous solution is and so there we have the solution for a simple harmonic oscillator. Is that what things look like in class? E to the I omega t? No, it's not. Are either of you familiar with e to the I omega t? Or Euler's relation? Then let's look at Euler's relation. So here we've just gone through all the work that we've done. Oh my goodness. I divided by m and forgot to put over m here. That's bad.
Yeah.
Come on, oh no. You must load. That's no darn good. Okay, well, I don't know what was on that page, but clearly we're past there because we now have our solution. Omega, I called it omega 0 here because when we go to the damped case, we're going to have a different omega. Is square root k over m. And this here is what I just wrote. I think. Did I use A and B or A1 and A2? I don't know. They're just constants. So here's Euler's formula. Euler determined.
What was that equation? Oh, never mind. It's right there. I see it.
Euler determined that e to the I times some angle, omega t is our angle in this case. I just put theta here because this is the general Euler relation. E to the I theta is cosine theta plus I sine theta. So when I have that homogeneous solution of A e to the I omega t plus B e to the minus I omega t, I can replace that with, well, let me show something in between. These are all correct on the line below, but I'm going to show something in between just for clarity. A e to the I omega t plus B e to the minus I omega t is equal to A times cosine of omega t plus I sine of omega t. So that's substituting in Euler's relation. But we have some good trig knowledge. What is cosine of minus omega t? I want to get it into plus omega t. So how can I convert from minus omega t to plus omega t with a cosine? Cosine is an even function, which means it's symmetric about 0.
There's a rule about this.
Wait, what are we wanting to do?
We want to replace this here with something that's a function of plus omega t. Because these over here were functions of plus omega t. So cosine of minus omega t, if it's symmetric about 0, then cosine of minus theta is equal to cosine of plus theta. That's what it means to be symmetric about 0.
Right.
And so this is exactly the same as if it was plus omega t.
And is that the same with sine?
No, because sine is anti-symmetric.
That's right.
And so the sine, I have to bring the minus sign out here. Sine of minus omega t is minus sine of omega t. I did that so now I have the same trigonometric functions in both terms. And so now I can combine these. A plus b cosine of omega t plus I a minus b sine of omega t. Now I have an I out front, but there was no rule that said A and B had to be real values. The rule is that my actual x value has to be real. And so I look at this, cosine is always real. Sine is always real. That means A plus B must be a real value, and I times A minus B must be a real value. Otherwise, I would have imaginary displacement. So all we do is we say, let us simply rename this as C and rename this I, A minus B, as D. And these two are completely independent. The A plus B and I, A minus B are completely independent. I'll actually show you why. We're never going to get through the lecture because I keep showing you more and more. But if A is equal to A0 plus IA1, that's a complex value, and B equals B0 plus IB1, then if I do A plus B, that's equal to A0 plus B0 plus I times A1 plus B1. And we have the rule that this has to be real. If this is real, that sets a condition on A1 and B1. For this to be real, A1 plus B1 must equal 0. So A1 equals minus B1. And so now I'm going to replace this with...
Can you go over those that red bit again?
Yes. This here has to be real.
Right, that must be real. I get that.
And so if that's real, then that means that the thing that I is multiplied by has to be 0. Sorry, was I standing right in front of what you need to see?
Yes.
Right, since I is multiplied by A1 plus B1, for this thing to be real, all of these constants here were reals when I broke it into the real part and the imaginary part.
Okay, I understand.
And so this here is real.
The imaginary number times 0 makes it real.
Correct.
So A plus B has to be 0, so A is negative B.
Oh.
Thank you for explaining to both of you.
Anything times 0 is
Right.
So we have that relationship that says between the A1 and the B1. And then we have our second condition that I times A minus B must be real. And that's equal to the minus is because I had I times I. And if
isn't I times I squared, which is -1?
right, that's why there's a minus sign right here.
Oh, right. Okay.
Because that's I times I.
Hold on. Let me figure out.
Okay, let me not go quickly.
So I times A minus B, where'd you get that part from?
That's looking at D.
Okay, we're looking at D now. So we already looked at C.
Right. And so here I've done it explicitly. Well, not as explicitly as I could have. I suppose doing it the most explicit. I'll do it the most explicit. So notice I put the minus IA1 instead of plus IB1. And so now if I take these, I'm going to have equals I times A0 minus B0 plus I squared times A1 plus A1. Right, there's this I and this I for the first one, this I and this I for the second one. That's a minus and a minus, which made that a plus.
Hold on, let me work that out. So that's going to be I squared minus I squared what, huh? Oh, okay, so that's why that's plus. Okay, I get it. So then can't that just be minus 2A1?
Yeah. And then we have D must be real. And since D must be real, that means that I must have A0 minus B0 equals 0.
Right.
So A0 equals B0. And now I come back here. And so A was A0 plus IA1. B is A0 minus IA1. And your value of C depends on just A0, and your value of D depends on just A1. So you end up with D is minus 2A1 and C is equal to 2A0. So you can directly transfer between the forms shown here and here. That's what I just showed you.
Okay, so what was C and what was D again?
C was 2A0, D was minus 2A1. It's not important to have that relationship. It's important to know that C and D are independent, A and B are independent, and you can relate A and B to C and D.
Okay.
Now this last form, anytime you have a cosine with one factor and a sine with another, it's kind of like, Randy, you've been doing phasors. You have the real part and the imaginary part. You use the Pythagorean theorem to find the magnitude. So you can combine these where F is equal to the square root of C squared plus D squared. And then phi is inverse tangent of D over C. So you can combine these into one sinusoid instead of having two, a sine and a cosine. The end result is we have sinusoidal oscillation. When you look at this final form, you have this F is the amplitude, and then you have the oscillation as a sine wave. So what we've shown in our first half hour of class is the solution for the undamped situation is exactly what we've been talking about in class. Now I have this as a cosine wave. You can have it as a sine wave because that's only shifting where time equals 0 is. That's all that's changing when you shift from sine to cosine. So that's an undamped oscillator. That's what we've already seen in general physics. Now we go to a damped case. Now the damped case, we have a damping force, and that damping force we learned long ago, I put a question on this on the final exam, that if you have something moving in a fluid, you have two possible forces. You have a drag force or a Stokes law drag. One of them is proportional to the speed, one of them is proportional to speed squared. For slow speed, such as what we have here, that damping force is proportional to the speed. And so we say that our damping force vector is minus BV vector. Minus because it's in the opposite direction of the velocity. And so now if I apply Newton's second law, it's going to look just the same. There I put X double dot instead of A. Except for now we have three forces. So our three forces are going to be directions minus kx minus mg minus b x dot. X dot x vector dot is to put the vector sign to make that.
Whoa, what, huh?
I just zoomed in so I could write this more carefully. There. Since velocity is the derivative of x with respect to time. Don't ask me why a stroke just disappeared. I trust it's going to reappear. I trust. I may trust too much because it hasn't reappeared yet. Okay, so this should be equal to
G, no.
That's equal to mx double dot, the other side of the equation. So, just like before, we rearrange this so I have x double dot plus k over m. Oh, wait, actually, I wanted the b first. Plus b over m x dot plus k over m x equals minus mg. Oh, once again, I forgot to divide the m. Equals minus g. So what's different between this equation and the one we did before? The one we did before didn't have the first derivative part. Otherwise, it's identical. Everybody with me? So what? So now we want to find the solution to this. And so what do you suppose the form to the solution of we're going to find the homogeneous solution again because the particular solution is just going to give us an offset on the x, a constant offset. What do you suppose the homogeneous solution looks like here? What's the form? Ooh, I used B before. Can't use B now because B is taken. So let's put e to the ct. You saw that on my notes I had ct on the previous one. The reason I had c was, of course, because B was going to be used down here for something different. So x is equal to e to the ct. We've already taken this. What's the first derivative of x then?
First derivative of x.
Yep.
C e to t. E to ct. Dx.
And what's the second derivative?
C squared e to the ct. So c squared x. C squared x.
So if I plug these into my homogeneous equation, I'm going to have c squared x minus b over m x minus k over m x equals 0. I forgot the c right here. Now, how do you find C? Well, first, let's factor this like we did before. How do you find C now? We have two situations that will make this true. What are the two situations that will make it true?
Or X is 0.
X is 0, or
the other stuff is 0.
or the other stuff is 0. And did I changed my signs again? Look at that. I am so consistent. These are all plus signs here, except for with the minus G. And I put them as minus signs again. Plus, 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 plus. It's pretty embarrassing. But it's just copy error. So I'm going to have C squared plus B over M C plus K over M equals 0. How do I find C?
Move everything else to the side, square root plus or minus.
That's right. Which we generally rewrite equals minus B over 2M plus or minus the square root
So say the quadratic form.
like this.
Why is that not minus negative 2? Minus 2. Okay.
Because when I put the 2 inside the square root, it becomes a 4. Which is why this is over 2 squared, because it's 4.
And then the 4 disappears because it's 4 over 4.
Right. Making some substitutions, we often call, come back to me, we define omega 0 is square root of K over M, and alpha is equal to B over 2M. Alpha, I learned to call it the Neper frequency from electronics, but it's a decay constant. And so if I put those in, this is equal to minus alpha plus or minus the square root of alpha squared minus omega 0 squared. Now this is interesting. We have minus alpha. That's real. And then we have plus or minus alpha squared minus omega 0 squared. Alpha depends on B and M. Omega 0 depends on K and M. So depending on your values of K and B and M, the thing in square root could be negative or positive. And so we have 3 possible cases here. Not just 2 like we had before. We have 3 cases. We have case 1. Alpha is greater than omega 0. If alpha is greater than omega 0, then this square root is a real value. And so I'm just going to have C is equal to negative alpha, well, C1 is equal to negative alpha plus square root alpha squared minus omega 0 squared, and C2 is minus alpha minus square root of alpha squared minus omega 0 squared. And when we put those into our solutions, then x1 is equal to e to the minus alpha t e to the square root alpha squared minus omega naught squared t, and x2 is equal to e to the minus alpha t e to the square root minus alpha squared minus omega naught squared t. Note that that square root term is always less than alpha because it's square root of alpha squared minus something. And so you're always going to have an exponent that is a net negative exponent, which means you're going to have a decay no matter what. It's never going to grow, which is kind of good because if you're taking away energy, you don't expect the energy to grow.
True.
We call this case underdamping. So this was case 1, underdamping. Or excuse me, overdamping. Wow. Somebody shoot me. Overdamping because B is large. And the overdamping case, you just have exponential decay. What happens if I plot an exponential decay?
It should be a downward curve, right?
It's just going to be something that goes like this and asymptotes to 0. So this is my x as a function of time is just going to go like this and asymptote to 0. Now that's one case. Because you have a linear combination of these two things, you can have the, I should have put an A here and a B here. You could have like x1 is positive, or A is positive and B is negative. And so there are other options. Another option you could have, for instance, would be something that goes like this. It can cross once because you have those independent A's and B's. But then it's just going to come to 0. So that is the overdamped case. It's going to come to 0. It's not going to oscillate at all. It can cross 0 once. The next case I'll look at is indeed the underdamped.
Where alpha is smaller than omega.
And then we define omega r is equal to the square root of omega 0 squared minus alpha squared. Notice that I reversed the order of alpha and omega to make it so this is going to be a real value. And then we're going to have C1 is equal to minus alpha plus I omega r, and C2 is equal to minus alpha minus I omega r. Because we had a plus or minus for the square root term, which is the omega r term here. This omega r is the resonant frequency when it's damped. Remember, we saw this oscillates at a lower frequency when it's in water. When I take it out of water, it raise it back up. Buoyant force. You know this thing doesn't float, but that buoyant force still exists. So it's a higher frequency when it's in air. So you can see why the resonant frequency is not the same. It's going to be a lower frequency than omega 0, the natural frequency when it's in air. And then we're going to have x1 equals a e to the minus alpha t times cosine omega rt plus, well, just put plus phi. It's the easiest way. And
Plus O phi.
yeah, for a phase shift. And that'd be phi 1. X2 is equal to b e to the minus alpha t cosine of omega r t plus phi 2.
Oh, it's plus cosine or minus cosine? Or times cosine?
Well, it's just times cosine. So we have an exponential decay and we have sinusoid for both of these. And so when we put these together, we just have x is equal to, I put in more variables than we need. I overcomplicated with my X1 and X2. So this is what our X looks like for the underdamped case. So if we plot that, it's going to be going something like, there's my C e to the minus alpha t
And then it's going to be
minus C e to the minus alpha t. And then inside of that
sinusoidal waves inside of those.
goes like that. So it's oscillating, but the amplitude is exponentially dropping. The third possible option,
There's three.
there's three.
So we got overdamped, underdamped.
We have alpha is greater than omega 0, alpha is less than omega 0. What remains?
Alpha is equal to omega 0.
That's right. We call this critically damped.
Does that just mean that it's not going to increase or decrease? It's just going to stay the same throughout?
No. And in fact, in this case, we would only have one value for C because we have plus or minus 0, right?
Right.
Well, DiffEq says, oh, we can't have that. Instead, what we're going to have is our solution is X is equal to A e to the minus alpha t plus BT e to the minus alpha t. That's the end. That's the end. So we have the addition of two exponentials. One is multiplied by time. And so if you draw graphs of these, it's actually going to look a lot like graphs of the underdamped.
Okay.
But what is different is that critical damping will asymptote to 0 the fastest. So critical damping will come to 0 the fastest. So if I open the door and I let it close, we have a damper on this. What kind of damping do we have?
Underdamped.
It's slightly underdamped. You're correct. How did you know?
Because it gradually slowed down fast more and more as the door got closer to close.
But it kept going.
Right.
It didn't asymptote to close. If it was critically damped or overdamped, it would have asymptotically approached, so it would have slowed down.
And then stopped
And
right
stopped.
before closing.
Well, it would have closed after an infinite amount of time if you want to be mathematical.
Oh.
Right? Because it's asymptotically closed. We want slightly underdamped, so it actually reaches close in a reasonable amount of time instead of getting really close and staying there.
Okay.
So it's very slightly underdamped. In our car shock absorbers, what kind of damping are we using? Yeah, it's underdamped again. We want it to oscillate a couple times.
And then stop.
But if it's like really low damping, it'll oscillate too much. So, how does your shock absorber actually work? What can you think of a way to design a shock absorber so that it will put a damping force on there?
Really spring, but it's shocks. So the gas is less than
Okay, but you can't just put a gas and compress it because that would act like a spring. What you need to do is you need to have something like this, like a plunger with a hole in it. And then the water, the fluid can go through that hole, but it's going to keep the motion both directions.
Mm-hmm.
And you make a bigger hole, and of course, it's not as much absorbing. Smaller hole, more absorbing. In reality, what happens when a shock absorber goes bad? The seals on that plunger go bad, it leaks more beside it, and so it has less damping. And so the B goes down because you're letting more go by. So we have three cases for the damped harmonic oscillator. We have, and this is just showing all of the work we've done, unique solutions. The underdamped case, here's an actual graph of underdamped. It looks a lot like what I drew, doesn't it?
Pretty close.
Pretty close, yeah. And then we have the actual case for overdamped. Here are three different graphs showing different levels of overdamping. The more overdamped, the longer it's going to take to reach 0. And then we have the critical damping, which this is showing all of them together. So you have critical damping is this color and overdamping is dashed, and then 2 examples of underdamped. All right, I'll see you for lab today, yo.
Wait. The red one is the critical damping, where it just kind of just goes and stops.
Yes,
Okay, and then the 2 solid black ones are the underdamped.
yes. And keep in mind, the door is doing something like this because it gets to 0 a lot quicker than the critical damped would.
Right.
It has small oscillations. Well, we had something that hit it, so it didn't do them, but it was coming slow enough that it, Oh, not again.
That was okay. Interesting stuff. Confusing as all get out. Interesting.